Session 2 is going to focus mainly on delocalized electrons and acid-base chemistry. Delocalized electrons meaning we're going to do a lot of resonance structures here. And acid-base chemistry, pretty sure Jeski might have started acid-base chemistry, right? I know Dr. Rai hasn't, but you'll learn about it today. Okay. Before we proceed, I want you guys to fill out the attendance code real quick. It's just for data. Some people.
The same as last time.
Yeah.
I see we got some new faces, so we're going to introduce ourselves. My name's Alexei. This is Jim. We both took Orgo. We did well in it, so we hope we can help you guys do well in it too.
You guys did the right thing to come to our OCI sessions. Hopefully it'll help you guys out. Did everyone fill out the QR code? Okay, then I'm going to proceed with the the session. We're going to dive straight into resonance. If I'm being honest, resonance is probably one of the harder topics in organic chemistry that you'll tackle, but it's very essential that you get it down and have a good understanding of it because it's going to show up throughout the rest of organic chemistry 1, and it's even more prevalent in organic chemistry 2. So it's important that you have this fundamental down. So without further ado, what even is resonance, right? Resonance, it's the movement of electrons, specifically delocalized electrons. And these electrons are going to be spread across multiple atoms, which is why we can form resonance structures. Resonance structures are important because it can provide stability, not stability. It can, when you compare two molecules using resonance arguments, you can tell whether one molecule is more stable than the other based on the charges and resonance structures you can make. It can also help with acid-base chemistry, which we'll talk about later on in this session. And it can help determine when you're doing equilibrium, acid-base equilibriums. It can tell you which way it will shift to, like towards the reactants or the products. And then lastly, it'll help with reactivity. And this concept is more geared towards organic chemistry too. So you don't have to worry about it too much, but essentially what reactivity is using resonance, you can make different resonance structures, meaning different resonance structures will have different reactivity and you'll form more desired products based on these different structures. All right, so that's the importance of resonance, but I'm going to be talking about the rules of resonance now. So resonance, like I said, it's the spread of electrons or the disbursement of electrons. So these electrons can either be delocalized or localized. Delocalized. Localized, as it suggests, means the electrons are local or fixed in a certain atom or a bond. So they can't share those electrons. But if we have delocalized electrons, that means these aren't fixed and these can participate in resonance and can sort of like disperse across other atoms. And these delocalized electrons can take in the form of pi electrons or lone pairs, pi electrons being double or triple bonds. Obviously, this pi electrons is going to occupy the p orbitals. That's an important concept. And then another thing is when we do resonance, only p orbitals, atoms with p orbitals can participate in resonance. So for example, if we have a sp2 hybridized atom, we know that there's going to be 3 sp2s and 1 unhybridized p orbital, right? The resonance will occur by overlapping p orbitals, so you need to do resonance essentially. Same case for sp. If we look at sp, we're going to have 2 sp orbitals and 2 unhybridized p orbitals. So these can definitely participate in resonance. Does that make sense? And you guys might already know this, but if we look at sp3 then, sp3 doesn't have any unhybridized p orbitals, meaning it can't participate in any resonance. So if you see any sp3 hybridized atoms and they're asking you if there can be any resonance done, it's just a trick question. There's no resonance that can be done, okay? So those are some general rules, and this last one is probably the most important one. And I'm going to be repeating this a lot throughout this session. But when you do resonance, you always want to start your error drawing mechanisms from a source of electrons, meaning you want to start from an area with high electron density and being able to move those electrons towards other areas with lower electron densities. And these high electron density atoms can they can take form in double bonds, triple bonds, negative charges, or lone pairs. These all have a surplus of electrons. And on the opposite end then, things like positive charges, single bonds, or hydrogen atoms, they don't have a source of electron they can share, so they can't participate in resonance. Well, I mean, they can, but you can't start your error pushing mechanisms from those. Because if we look at a positive charge, for example, let me draw this real quick. If we have this carb anion right here, you see that there's only 6 electrons around the carbon. And to participate in resonance, you need to have a surplus of electrons. And carbon doesn't even have a full octet. So if you take away more electrons from a carbocation, sorry, then it's just going to make it more positive, more polar, and more unstable, right? This argument can be made with single bonds as well. Single bonds are sigma bonds, right? So if we want to do resonance and we start and do an arrow pushing mechanism from a single bond, you're essentially just going to break that bond, which isn't good because you're not doing resonance at that point. You're just breaking bonds and making new molecules, which isn't the point of resonance. And hydrogen atoms, that's pretty obvious because they can only hold 2 electrons. And if you take those 2 away, then the hydrogen is basically expelled. So yeah, key point right here. Resonance always starts from a source of electrons. Does that make sense with everybody? Any questions? All right. So those are just the rules for resonance. And okay, we'll dive into some resonance patterns now. These are the 5 patterns you're going to need to know for organic chemistry. And it is as follows. I think we went over this last week as well, right? Yeah, so this may be a refresher for you guys, but allylic lone pair, you might be wondering what allylic even means. Allylic means the adjacent carbon that's next to a carbon double bond. So you see this carbon double bond here? The adjacent carbon would be this carbon. So this is an allylic carbon, and we have a lone pair on that allylic carbon. So it's called an allylic lone pair. And the mechanism for this, as you can see these red arrows, you take the source of electrons, make this a double bond, and then we take this double bond here and then make this into a lone pair. Pretty straightforward, right? Okay. The next one, we got allylic carbocations. It's like the complete opposite of a lone pair. Instead of a negative charge, we're gonna have a full positive charge. So since carbon has a positive charge, that means it's lacking electrons, so we can't start from that area. We need an electron source, which in this case would be this double bond here. So we'd take this double bond and move it right here to make a double bond here in this allylic carbocation. Pretty straightforward. Next one, we got lone pair adjacent to a carbocation, which is kind of like a combination between the last 2 you saw. So we're going to be working with 2 charges, a negative charge and a positive charge. And we always start from a source of electron, right? A surplus of electrons. So we're going to use the electron lone pairs on the oxygen molecule, bring it down, and make this double bond to form a carbonyl in this example. Next one, we got a pi bond between atoms of different electronegativity. This one's really easy. Essentially, all you want to do is compare the carbon atom here and the electronegative atom that's bonded to it. So you see how between carbon and oxygen, what's more electronegative, guys? Oxygen, right? Yeah, so since oxygen is more electronegative, it has more of a affinity towards electrons. It wants more electrons. So it's gonna pull these electrons from this double bond to itself and gonna create charges on both the on the oxygen and the carbon right here. And usually when we do resonance structures, it's not good if we make more charges, but in this case, this pattern is going to be valid because if we do, sometimes you can make more resonance structures from it because you create more charges. But yeah, a general rule though is creating more charges is bad during resonance. Got it? Okay, last pattern, conjugated pi bonds enclosed in a ring. This one is probably actually the easiest. You got a benzene ring right here, an aromatic ring, an arene, whatever you guys want to call it. It's a conjugated pi system, so all we got to do is move these double bonds to places where it didn't have a double bond, and that's how you get the structure. Make sense? Any questions? All right. So yeah, we're gonna do some practice problems now, resonance practice problems. And what we're trying to do here is we're going to draw the arrow pushing mechanisms, and we're going to identify what type of pushing mechanism what that was from the 5 we've learned so far. So I'm going to go through number 1 with you guys and let you guys do the other 3. So if we look here, this nitrogen atom has a lone pair that it can use for resonance since it's delocalized. Because we have a positive charge here on this carbon, it's lacking electrons. So we can take this lone pair, bring it, and form a double bond here, which would look like this. Okay, and then once we've done that, we see that the charge on this carbon would disappear because now this carbon here has a full octet, 8 electrons. But if we look at this nitrogen, we're now sharing that electron, the lone pairs with the carbon atom, making it more positive. So this positive charge from the carbon would shift to the nitrogen atom. Does that make sense? Anyone want to take a guess at what kind of pattern that was?
It's okay if you're wrong, just try and give us any answer,
Yeah.
whatever you think it is.
Better if you're wrong here than on exam, right?
Is it lone pair next to a carbocation?
Exactly.
Yep.
Lone pair adjacent to a carbocation. You're spot on. Lone pair adjacent to carbon. So yeah, that's what I want you guys to do for the next 3 problems here. If you need any questions, ask Alexi or me, and we'll come assist you guys. All right. So this one, we got a carbon anion here. That means this carbon has a lone pair, and we can do an allylic lone pair here because we can take this lone pair, make it a double bond, and then I'll not show it right here. And then we can take this double bond out and make this into a lone pair. So what is that going to get you? You're going to get you're going to get this structure, right? Some of you guys might be wondering, you could do this the other way as well, right? So let me code this. We can start from here and bring this down here, and we can take this double one and put it on here as well, which is going to get you double one here. Yeah. So these are the 2 resonance structures you can do. They both follow the same pattern, allylic lone pair. It seems like tedious right now to basically the same, but it's really important that you get into the practice of this because once we get into resonance hybrids, you need to know all the available resonance structures that we can draw so that we can draw all the proper charges and the dotted lines. So allylic lone pair. Okay, next one. We got a carbon ion again. What we can do here, we have a lone pair, or not a lone pair, sorry, double bond. So this is our source of electrons. electron, we can, this is a bit small. Let me kind of zoom in. We can take this and put this here to make a double bond. And that's literally it. So what would that get you? You would get this right here. And you can continue this again. You can take, it's a bit cramped, but if you take this and bring this here, that means we can get this structure. All the same structures, by the way, but like I said, it's good practice to draw all the resonance structures. So these are the structures, and this was a Lily cation because we have a cation and yeah, a Lilic cation. Is it cation or carbocation? A Lilic carbocation. It doesn't really matter.
Same.
Yeah, same thing. All right, last one. There's no charges, so you might be wondering where we start our resonance, but we got this double bond here. We can, there's a difference in electronegativity because we got a carbon and an oxygen. So we can take this double bond and bring it up to the oxygen. And you get this right here. Pretty sure, oh, 1 second. We got a charge. This carbon would also have a positive charge now. Does that make sense? All right. This would be a lone pair adjacent to a carbocation. No, my bad, guys. A pi bond between atoms of different electronegativity. I'm not gonna write that because that's too long, but you get the point, right? Pi. All right. Here is the key, if you're wondering. Same thing. Okay. This is also important, being able to differentiate localized versus delocalized electrons. So best way to tell if a source of electrons is delocalized or localized is if you can do resonance with those electrons, that means it's usually delocalized. If you can't do any resonance with those, that means it's localized. So for instance, let's look at this first example. We got a lone pair here, right? Is there any valid resonance structures you can do? Resonance patterns?
Any patterns? Thumbs up for yes, thumbs down for no.
See, couple thumbs up, couple thumbs down. Can one of the people who did thumbs up explain what kind of pattern you see?
Different electronegativity.
That's a good observation, actually. But we're asking about the lone pair on these oxygen, right?
Sorry.
Yeah, that's a good point. Because you can do resonance with these pi bonds here, but it's asking for the lone pairs. You can add some. So yeah, we can't actually do any resonance here, meaning it's gonna be localized.
Easy way to remember that is the electrons are local. They don't want to go anywhere.
Exactly. It's fixed in place, stagnant. Next one, we got this double bond here, right? Is there any resonance pattern we can do with this? Thumbs up for yes, thumbs down for no. Let's see. Why do you think there's a resonance pattern for anyone who wants to explain? We put a thumbs up. It's fine. It's fine. Okay. It's actually not. You can't do any resonance pattern. Although there is a source of electrons, there isn't any atoms here that lack electrons. They all have a full octet. So that means it's going to be localized. What was that again? Oh, you're asking like if we did like one of these? Yeah, we could. Actually, we can't do that because that create unnecessary charges. If we did that, we had a we'd put the negative charge. You don't want to create unnecessary charges, basically.
Only time you do that is between pi bond with atoms of different electronegativities. It's the only time you'll create more charges than there were before.
Make sense? All right. I'm gonna let you guys do the next two problems. Has everyone finished or close to finishing? Thumbs up if you're close to finishing or finished. All right. Seems like everyone. Okay. Let's go through these. We have a lone pair here. Does anyone want to give a shot as to what they think it is? Yeah. You're correct, because this lone pair here can come here to form a double bond between the nitrogen, and this pi bond here can go up and form a lone pair. Does that make sense? So because it was able to participate in resonance, that means that electron was delocalized. Good job. Let's go on to the next one. What about this electron here? Anyone want to give it a shot? Yep. Why is that? Exactly, yeah. You
know
can
the
do
name of that
resonance.
pattern? I wrote down all the patterns right there. It's a little cheat sheet.
It's like
Yeah, that one, the electronegative one, to the pi bond, right? No. I don't know
Yeah.
what that is.
yeah, it's that one. Pi bond between the difference in electronegativity. So we can actually bring this down.
I think it's
Oh wait, no, sorry. Lone pair adjacent to a carbocation. My bad. I was looking at it differently. Yeah, it's lone pair adjacent to a carbocation. So this would be also delocalized. Do these answers make sense to everybody? All right. Here's a key, same thing. All right, let's move on. We're going to talk about resonance hybrids now. Resonance hybrids, we've mentioned this a little bit, but resonance hybrids is a combination between every single resonance structure you can make or draw, which is why in the previous problems, I made you guys draw out every single arrow pushing mechanism you can think of. Essentially, resonant hybrids show the disbursement of electrons, and it's showing that these pi bonds are not localized. It's not going to be in one place. It's going to be moving around in the molecule. That's why, to indicate that, instead of a straight double bond, straight line like this, we're going to do dashed lines to indicate that the electrons are moving. And for charges, instead of writing full negative charge or full positive charge, we're going to use partial charges. You guys might remember them from maybe like dipole moments in water. This is essentially what we're going to write when writing charges. All right. Okay. So let's do one together. This isn't actually just resonance hybrid. It's asking you to draw all the resonance structures and then doing the resonance hybrid. So these ones will take a bit longer. These are the type of questions that they might ask on exams, where you have to draw all the resonance structures and then at the end, draw the resonance hybrid. So let's go through run together right now. So if you see here, we always start from a source of electrons. Our source of electrons available, this negative charge and this pi bonds, these pi bonds, right? But this negative charge is going to be a better candidate because it has a surplus of electrons.
Typically, you'd rather choose a source of electrons over a pi bond.
True. So what we can do here, I already see a pi bond here, so we can do a Lilic lone pair. Also, this is it may differ class by class, but some teachers are very picky with where you start your arrows. Because if you, for example, use your arrows to indicate like this, they may dock some points because it's not really the negative charge where you're getting the electrons. You get the negative formal charge because there are electrons. So sometimes they make you draw out the electrons here and then show the flow of electrons. So for your guys' sake, I'm going to draw in the electrons now. So yeah, we can do that. And then we can bring this pi bond out and then put it on this carbon to make a lone pair. So that's our first structure. That's ugly. Right here. And then the negative charge would then be on this carbanion. What?
Missing a pi bond.
Oh yeah, and this pi bond here. Oops. And then we can actually continue this throughout the entire ring. We can take these electrons and make this into a pi bond. Take this pi bond, make it into a lone pair. So what can we get? We can get another resonance structure. And then the negative charge would be here again, once again. And then we can continue this around the ring again by bringing this and making a double bond here. And then bringing this double bond, making this into a lone pair. And by the way, these are all allylic lone pairs, the same patterns. And then you can do it once more again. I know it's a lot of resonance structures, but these are the type of problems that are going to require you to do. Take these take these electrons, make a double bond, take this double bond, make it into a lone pair. Actually, yeah, I'm gonna show that at the last, after the ring itself. And then that's for, we can do one more here. Yeah.
Yeah.
And then we can do another one here. Bring this one here. And then this charge here. Make another resonance structure. And then from here, what you can do is you can take these electrons and do resonance patterns with this carbonyl group. So what you can do is take these electrons, make it into a double bond, and take one of these pi bonds from the oxygen, and then place it on top of the oxygen. This would also be yeah, question?
Bring you back to the starting one.
Yes.
Yeah, this one, yeah, this pattern here. Yeah, to be honest, we could end it here. And then we can just go back here and then do the pattern here, but I'm doing the same thing from that pattern, so it really doesn't matter. Yeah. We can do that. What was that? yeah, take these electrons, make it into a double bond, and then we can get our final resonance structure. Oxygen. So, yeah. So this would be 5 resonance structures, right? This would be 1, 2, 3, 4, 5 resonance structures. Yeah. So in this case, we would have 5 other resonance structures we can draw. This includes them all. And then it asks for the resonance hybrid, right? So it's going to be a combination of every single resonance structure we just drew. So it might be hard to wrap your brain around, but here, I'll show you. What we do is first draw the structure without any of the double bonds. Oops. Right? And then wherever there was a double bond, for example, there's a double bond here, 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 basically around the whole ring, right? So we can actually draw dotted lines to show that the double bonds were everywhere. And then there's also a double bond right here. So we can draw dotted lines here. And then there are double bonds on this oxygen, right? This carbonyl group. So we can draw another dotted line here to show the flow of electrons. So that shows the flow of pi electrons. Then all we got left to do now is to show the partial charges. So partial charges is pretty easy. Wherever there was a charge, you just put a partial charge. So for example, there's a partial charge here, right? Partial negative. So we'll draw a partial negative here. There is also another charge here. So we can draw a partial charge here. There is a charge here as well. So we can draw a partial charge here. Partial charge here as well. So another partial charge. This one, there's another one here. So we can draw this one. And then there was another charge on this oxygen molecule. So we also draw a partial charge for this oxygen molecule. And yeah, that covers everything and how to draw a resonance hybrid. It's a bit complex, but it gets easier once you draw a lot of these. To be honest, this is like, usually you don't have to draw this many resonance structures. You'll usually cap out at like 3 or 4 resonance structures, but this one had a lot. So yeah, this was on the harder end on resonance problems. Does that make sense to everybody? Or do I need to clarify? Repeat any parts? You guys kind of seem confused. Are you guys telling the truth? Okay, why don't you guys just try it out then? Just try out one of these problems and we'll help you walk through them. Let's do this. Since I don't have room, I'm gonna erase this structure, this resonance pattern. So if you want to take a picture right now, you can, but I'm gonna erase everything here.
Our sessions are recorded though, so if y'all want to see this later, you can go to the link, we'll send it to the group chat.
Yep. We post these on YouTube, by the way. All right, I'm gonna delete this now. Bigger issue. All right. Let's try this. So, like I always said with resonance, you got to start from a source of electrons. And our source of electrons currently are these pi bonds and this lone pair on the nitrogen. So we can start from either one, this lone pair or the nitrogen lone pair. So what we can do here is an allylic cation, where we take this pi bond, bring it here, and that's it. And you're going to make a new structure here. then you're going to shift that positive charge from here to over here. That's one way. We can also continue this because we see an adjacent double bond, right? So we can take this again, do another allylic carbocation. And then the positive charge would be shifted to this N terminal carbon. Now, like I said, we could also start from the lone pair, right? So I'm going to go back to the original structure, and I'll use a different color to highlight the arrow pushing mechanism. But we can take this lone pair, oops, and then we can make a double bond here, actually, is nitrogen, which is going to make that. And the positive charge is now going to be on the nitrogen. So these are all the valid resonance structures. And to show that these are all the structures you can do a bracket like this, and then point it towards a resonance hybrid. And like I said, resonance hybrid, you just draw the structure without any of the double bonds. I think that's correct. Yeah, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Yep. All right. And then we're gonna draw the dotted lines wherever there was a double bond. So we see there was a double bond on basically every single, carbon here. So we can do, I'll show it in different colors. Right? We can do that. And that takes care of the double bonds. And now we just got to put in our charges. So if we look, there's a charge here, a charge on the nitrogen, a charge on this carbon, and a charge on the terminal carbon, right? So just put partial charges for those spots. So partial positive, partial positive. Hold up. Yep. And then partial positive right here. And another one at the very end. And that's going to be your resonance hybrid. Any questions? Make sense? Thumbs up if you get it. Good stuff. All right.
For the first one, we can probably do the pi bond between atoms of different electronegativity, right? So we move pi bond like this. There will be a negative charge on nitrogen, positive charge on this carbon, oxygen, like this. So, and then there are two lone pairs on the oxygen, so you can probably do lone pair adjacent to carbocation. And since we don't have anything here, we cannot move this positive charge anymore. So now let's think about the pi bond between carbon and oxygen. We can probably move this double bond onto oxygen, right? Nitrogen. So when you move that, there will be a single bond here, minus charge, positive charge. And now you have an allylic carbocation, right? So minus plus like this. All right. So I think these are all resonance structure that we can get. So I would say for this part, you can also try and combining these two arrows. Maybe you can try doing like this, like this. You can also do that. Both are fine. So now let's take a look at the second one. So for the second one, let's start with the negative charge. we can probably do electric lone pair, right? Like this, like this. Negative charge here. Positive. 1, 2, 3. We can keep moving that negative charge because it's participating in electric lone pair. 1, 2, 3. There will be a negative charge. This is negative charge. There's a single bond and then double bond. So now we can do it like this, like this. What are we doing? Hydrogen. Yeah. Okay. And then we can probably do something with the triple bond, right? Because triple bond also has a pi bond. So now let's take a look at this. So now we move negative charge onto this carbon. And then one of the bond from triple bond will move onto this carbon atom. So now there will be a double bond here. And also you shouldn't forget the carbon atom here. So you can show it as a dot like this. So now since one of the bond move onto the carbon atom, there will only be 2 bonds left. So now the negative charge is on here. That is how we deal with triple bond. And also you can probably start moving this positive charge around the resonance, and I think you can do it. So I'll skip that part right now because we have a lot of steps to cover.
Use another triple bond, we can put double bond with the minus charge.
Because we have three single bond or triple bond, right? So one of the bond move onto the carbon atom and it becomes a lone pair. That's why we are left with double bond.
So you just keep 2 pairs and then attach
Yeah. So we move one bond from triple bond onto the carbon atom, and then the bond became a lone pair. That's why we have a negative charge on that carbon atom. Yeah.
I think this is the, okay, yeah. This is the last subtopic on resonance. And it's being able to identify which of the resonance structures is most significant. And you just follow these 3 points. First point, the most significant resonance is going to have the greatest number of field octets. So if we look at this example here below, this oxygen here has a full octet because there's 8 electrons. But this carbon here has a positive charge, right? That means it's lacking electrons because we only have 1, 2, 3, 4, 5, 6 electrons. It's not a filled octet. However, if we look here, although the oxygen has a positive charge now, it still has 8 electrons around it. 1, 2, 3, 4, 5, 6, 7, 8. So that's still a filled octet. But now carbon also has a filled octet because there's 1, 2, 3, 4, 5, 6, 7, 8. Since carbon, in this resonance structure, the carbon has a filled octet, this is going to be the more significant resonance structure, or in other words, it's the more contributing resonance structure as well. So yeah, when you decide which of the resonance structures is more significant, the first thing you look for, every atom have a filled octet. Next, we can look at the structure of the formal charges. And it's basically saying the structure with fewer formal charges is more significant. So if we look at this, the first atom, the first molecule here has no charges. The second molecule has 2 charges, a negative and a positive. The third molecule also has a negative and a positive charge. So we can automatically say and crown that this structure here is going to be the most significant because it has the least amount of charges. So you might be asking then, how do we differentiate and rank the last 2 when these both have the same amount of charges? Well, we can go back to concept 1 of filled octets. And if we look here, the positive charge is on nitrogen, but it's still going to have a filled octet. and this nitrogen is also going to have a filled octet. But if we look on this one, the negative charge is still on the nitrogen, so that's a filled octet. But this carbon here, it's a positive charge, a carbocation, meaning it's not a filled octet. Place it as the least significant resonance structure. Make sense? Yeah, so you got to use a combination of these sometimes to really figure out which one is the most significant or not. All right, last one is using the concept of electronegativity. And we just look at if there's a negative and on the more electronegative element, that means it'll be more significant. And conversely, if there's a positive charge and it's on a less electronegative element, that means that will be more significant. So for the example below here, we're going to be working with a negative charge. The negative charge here is going to be on oxygen, which is fairly electronegative. But on this one, the negative charge is going to be on the carbon. And we all know that oxygen is more electronegative than carbon. So the charge will work better with the oxygen molecule. That's why this structure here is going to be more significant of a resonance structure than this carbon ion. If we look at this one actually has a positive charge. And like we said, if there's a positive charge, it'll be more stable on the less electronegative element. So in these two examples, there's a positive charge on the oxygen and a positive charge on the nitrogen. And if we look at the periodic table, nitrogen is less electronegative than oxygen. So that make this a more significant resonance structure than this. Understood? All right. Let's do some practice problems.
We just do like 1 and 2.
Yeah, let's do 1 and 2.
Just do 1 and 2. Don't worry about 3 for now.
You guys want me to walk through one, or you think you guys got it? Thumbs up if you want me to walk through, or thumbs down if you think you got it on your own.
I got it.
Okay. I'll walk through one with you guys. So let's see here. If we look here, this molecule has filled octets everywhere. This one has a filled octet. But look at this one. This one has a positive charge on a carbon, meaning it's an unfilled octet. So this would automatically be placed in third, least significant. Next, we got to compare these two. And we can already tell because this one here, it has more charges, making it more unstable. So then we can rank this 2, and then this automatically becomes 1. So this is second most significant, and this is the third. Does that make sense? Do you guys understand my thought process behind how to approach these problems? All right. Then these ones should be fairly quick. So you can try 2 and 3. Any questions? Ask us for. Water. This question is to focus on carbocation stability and not induction. Or carbocation stability. What does it mean by that?
Like 1, 2, 3.
Yeah, I did it in the bottom. Like 1, 2, 3.
Like, just so we can, I think we can like ask them to order.
Oh yeah.
Yeah. Does anyone want to answer question 2? Anyone think they got the answer? We know that one? But yes, do you know why?
Because you don't want to charge on carbon, like on two, and then oxygen is more electronegative than nitrogen. So you want a negative on the oxygen.
That's right.
Mhm.
What about three?
Yeah. So this one, the answer was 3, 1, 2. And by the way, I think I heard you say that there's a negative charge on the carbon. That's why you excluded it, but it's fine to have a charge on there because it still would have a full octet. It's when it's a carbocation that is not going to have a full octet, and that's when you can exclude it automatically. Okay? Yeah.
It's just that carbon is the least electronegative out of all three of them.
Mhm.
Yeah.
So this one was basically testing your idea of electronegativity, your understanding of it.
Do we remember how electronegativity works in the periodic table? You got that?
Anyone want to give a shot for number 3? Let me ask it this way then. Who thinks 1 is the most contributing? No one? Who thinks, oh, Ashton. Who thinks 2 is the most contributing? Okay. Who thinks 3 is the most contributing? Okay. So it was between 1 and 2, from what I saw. And it'd actually be 2 in this case. Because why is it 2?
Charges on the oxygen.
Right?
Stabilize it.
All right. The positive charge is on the oxygen, meaning that it can stabilize it more because it's more electron donating. No, not electron donating. It has more electrons, so it can stabilize the positive charge better. Sorry. And number 1, honestly, we can exclude this automatically because it's a carbocation, meaning it's an unfilled octet. So this is automatically 3rd place. This is also actually a carbocation. So
Also has an unfilled.
yeah. So actually these 2 would be our main discussion. This would automatically be the 1st place since it has full octets on every atom. But to differentiate between these 2, you got to look at where the positive charge is. So on this one, the positive charge is next to oxygen. And on this one, the positive charge is like quite far away from oxygen, right? Oxygen, because it has a higher electron density, it can better stabilize the carbocation on this carbon right here. This one is quite far away, so it have a less of that effect. So this would be less stable. All right. So, oops. So if we had to rank them, 2 would be the greatest, and then 1, and then 3. Does that make sense? On 1, this carbon, what'd you say? Yeah, it doesn't have a full octet. So this is a candidate for last place, but if you also look at this one also has a carbocation. So this one also doesn't have a full octet. So I was just differentiating between which one comes in last. Mhm. Does that make sense? All right.
Okay, so on to acids and bases, and pull it back up. So first, we need to know our types of acids and bases. This is just something you memorize, like it's not that much to know. So to start, we have Bronsted-Lowry acids and bases. So Bronsted-Lowry acids are defined by donating protons. And then Bronsted-Lowry bases are, yeah, they accept protons. So that one's kind of easy when we think about like, it's where the protons are going. That's pretty easy. And then we have Lewis acids, which those are defined by accepting electrons. So it's a little different than what we normally think of, but yeah, just commit to memory. And then Lewis bases donate our electrons. Does that make sense between those two? Okay. So another thing that we need to know when we're looking at acids and bases is their pKa. So pKa is kind of a value that measures how acidic something is. It sort of measures a willingness to give up a proton. So when we're looking at, you're typically going to see these charts when you're dealing with pKa's. And the lower an acid's pKa, the more acidic it is. Luckily, on this little table here, we have little arrows with strongest acid and strongest base on it, so you can keep track of which one is which. But always know the lower the pKa, the more acidic. So if it's a more acidic molecule, that also means it's going to be less basic. Those are kind of the same thing. So on the other side, if we don't have low pKa and instead we have high pKa, that means that we have a weak acid and a strong base. And this is just really important in knowing where our equilibrium is going to land in an acid-base reaction, whether we're going to favor products or reactants. So next we're going to be comparing our acidity and basicity. The more stable a molecule's conjugate base is, the more acidic the molecule is. That one's confusing sometimes when you're first learning about it, but if you want to know if a molecule is acidic, look at how comfortable its base is, right? If we can take that proton away and be left with a negative charge and it's comfortable, then that's acidic, that's good. But the more unstable that conjugate base is, that means it's not that willing to give up the proton. So it's going to be more wanting to take that proton back. And then our conjugate bases are considered stable if they are effectively able to distribute and delocalize that negative charge around the molecule, which kind of, it just stabilizes them. And so that comes into knowing our resonance, which is very important. We just learned that. So we normally use a acronym, that's what that's called, to think about the conjugate bases and how stable they are. And the acronym is ARIO. So if we're looking at ARIO, A is for atom. That is kind of just telling how electronegative the atom that the charge is. So if we start with an acid and we take our proton away and we're left with a negative charge, if that negative charge is on oxygen, that's a good thing. That's stable, pretty acidic. However, if that negative charge is then left on a carbon, that is not that electronegative, not as stable, not as acidic. The next thing we're going to look at is R, which is our resonance. So we just talked all about resonance. If our negative charge that we leave behind is able to resonate around the molecule, that's more stable, meaning that molecule is more acidic. Next is induction. This is just if we have electronegative atoms that are nearby. So not that our charge is directly going onto those electronegative atoms, but that they are nearby and able to kind of take on some of the weight of that negative charge. That's very stabilizing. And then lastly is orbital. So the greater the S character that we have, the more stable it is. Do you guys have any idea what like S character means?
The amount of the S bond.
Doesn't one like pull it closer than the other?
Yes. So if we're thinking about like S character, we think about the hybridization of that atom. So our different types of hybridization that we talked about, we have our like SP, which is linear. We have SP2, which is able to do resonance, and we have SP3, which cannot do resonance. But if we have SP, that is more S character than SP2, right? So our S little orbital is just a little round ball around our nucleus. So that means that all of our electron density is pretty close to our nucleus. Once we add more P character, our P character is like the dumbbell looking things. That pulls our electron density kind of further from our nucleus, which is less stable. So if we have more S character, it's more like a ball in shape, closer to our nucleus, more stable. Does that kind of click?
Yeah, so the more P's you have, less stable.
Yes. And normally when you're looking at it, orbital is kind of the last thing you'll be looking at. The acronym ARIO, you go in order of the letters. So you're gonna look at atom first, then resonance, then induction, then orbital. And we don't mention it, but another thing to also look at is our charge. So if we have charges, that's obviously less stable than not having charges. So some people also call this like cario or cario or just ario, but look at charges first before you get into the rest of this. Yeah, so here are some figures that just kind of help you look at what's going to be more acidic or less acidic. So yeah, if we look at the acidity, no, the electronegativity of the atoms that our protons are connected to, we can see that the more electronegative that atom is, the more acidic our protons are going to be. So here are like fluorine is the most acidic. Right? Because if we're removing that proton, we're left with a negative charge on that fluorine. Fluorine loves a negative charge. Atom size, again, that one, the bigger our atom, the more able it is to stabilize that charge. So then sulfur would be more comfortable. If we look at our inductive effect, the more electronegative our atoms nearby are, the more stabilized our conjugate bases, more acidic. Hybridization. This one is like we were just talking about, that's our S character. So having more S character is more acidic. So that one I'm gonna write down here because I personally always struggled with orbital. So I don't know if you guys are kind of feeling the same way, but that one just, I don't know, it doesn't make as much sense as the others. So if we're looking at this triple bond here, that's most S character. This is less S character. Right, and that's because we have SP versus SP2. And then over here, when we have resonance, more resonance capabilities, that's always going to stabilize our conjugate base and make it easier to lose those protons, making it more acidic. So here, if we have a carboxylic acid, if we remove that proton and we're left with a negative charge, that negative charge is then able to move around and place charge up on the top oxygen as well as the bottom oxygen. Whereas on the alcohol, it's just stuck in place. Which, yeah, it shows right there. And yeah, I kind of just talked about these. So yeah, our electronegativity, more electronegative, more stable conjugate base, more acidic. The size of the atom, the larger the atom, you can better distribute that negative charge, more acidic. So here we're going to get into some practice. So for these ones, just circle which side you guys think is going to be more acidic. So on the first one, what are we thinking? Is the red side or the blue side more acidic? Blue side, correct. What's our reasoning for that one? Exactly. So we're gonna want, no, I'm not on drawing. Okay. We want our more electronegative atom to be getting that charge when we're losing our proton. So that would be right. What about the next one? Red or blue side? Blue. Correct. I rock with that. Again, we want our negative charge to be going on to our more electronegative atom. And so if we're looking over here, that would put oxygen as more electronegative than carbon. So that is good. What about the last one? Blue as well? Oh, no. I agree. So this one is not focused on electronegativity as much as our size of our atom, like we talked about. The bigger our atom is, the more kind of distance we have to move that negative charge around and get some stabilization going. So that one would be blue. Alrighty, so next we're gonna look about how resonance affects our acidity or basicity. So again, like we said, if we are able to delocalize that charge and move it around by spreading it out, we stabilize it. And so if we stabilize the charge, we have a more acidic proton. Also, something to consider with this that might be kind of confusing is that when you're looking at resonance, it's not just how many resonance structures you can make that's important. It's the actual like significance of those structures. So like we talked about, when you have structures that have no charges, that's great. If you have structures that are full octets, that's going to be better. So if we are able to move our charges around in ways that are more significant, that's often going to make more of a contribution than having resonance that's like okay. So that's something to consider when you're looking at your acidity. So here's some more practice. How are we feeling about the first one? Blue or red? Blue. This isn't intentional. These all you keep ending up blue. Why is it blue versus red?
So the PO rules, that's what rules. Are to do this way.
So this one, it's not necessarily about our orbitals. Good thinking on that though. But here we can more directly think about our resonance as being a bigger contributing factor in our acidity. So if we take away our protons, that leaves us with these two structures. Right? And if the structure on the left, we can't do anything with. That negative charge is just stuck on that oxygen. Enough said, that's done. But on the right side, we can take this negative charge and we can push it up and push it up onto that other oxygen, right? So now we have our charge spread between two oxygen atoms, which are both electronegative. And then we also have resonance going on. So that's going to be like significantly more stable than just the alcohol. What about the second one? Also blue. Okay, why is this one blue? Same thing, same thing. Over here, we get a negative charge, can't do nothing with it. Over here, our negative charge can be pushed up to that oxygen again, and we're resonance stabilized. Alrighty, so here are the last two, I think the last two things to consider when we're looking at our acidity and basicity. Our inductive effect, like I talked about a little bit before. Our induction is kind of just based on whether or not we have electron withdrawing groups around it that can sort of stabilize that charge by having an inductive effect where they're sort of pulling some of that negative charge towards themselves, right? And so having an electroatom nearby is significant for that, but also having multiple electronegative atoms nearby. So if you have one fluorine next to your charge, that's not as good as having two fluorines, which isn't as good as having three fluorines. So those are kind of going to affect it. And then also just how electronegative the atom nearby is. And then we also need to look at our hybridization. Like we talked about, that's our S character. So the more S character we get, the better that is. That means also the less P character we have. So if we look at the first one, what's the triple bonded one called? What's that hybridization? We talked about it a little earlier. SP? Beautiful. Yep, that one's SP. And then what about the next one? SP2. And the final one? SP3. So yeah, when we have less P character, that means we have more S character, which is good. Right, and that more S character leads to our more stable base. I think I just moved one. Yep, so let's try with this how our induction or hybridization affects it. You're talking, so I'm guessing that's good. For the first one, what side? Yes, it is. And what's our reason for that one? Yep. Yeah, so here we have these three chlorine groups, which are all very electronegative. all kind of pulling some electron density towards themselves and stabilizing our charge in our molecule. Whereas on the other side, we still have the same resonance abilities, we still are on the same atom, but we don't have that induction. So that makes the blue side more acidic. What about the next one? Blue. Also blue. What's the reason on this one? Yep, we again have our electronegative atoms that are nearby. Inductive stabilization, more acidic. What about the final one? Also blue. And this one is again that we have SP on our triple bond, whereas we have SP2 over with our double bond. So if we have SP hybridization, that's more S character, our electrons are closer to our nucleus, and then it's more stable, so more acidic. So when you're looking at hybridization, you want to look at how many different electron like domains or like electron groups are around it. So if you look at we'll look at the like end carbon right there. So if we look at that, we have two electron domains, one of which is the hydrogen and the other is our other carbon that we're triple bonded to. But there's only two separate groups that we're connected to. So if we have two separate groups, that's SP. If we have three separate groups that we're connected to, like this carbon over here, we're connected to a hydrogen, double bonded to a carbon, and we have another bond to a hydrogen that we can't see. So that's three different groups. So that's SP2. Does that make sense? But if we look at our carbon up like here at the top, that is going to be SP3 because we have four different groups that are around it. So it's going to be SP, SP2, SP3. Does that like make sense? Okay. And then sometimes it'll like trip you up if you're seeing something that has three different electron groups around it. So you're like, oh, that's gotta be, or four different groups on it. So you're like, oh, that's SP3. But if they're delocalized, it's SP2. So anytime you have something that is able to do resonance on it, that's SP2. So just keep that in the noggin for future. Alrighty, so now we're gonna use all of the knowledge that we just conjured up on acids and bases to figure out which side of our equilibrium, or yeah, which side of our reaction is favored in equilibrium. Do you guys understand what it means to say it's favored in equilibrium? Understand? It's okay if not. So if you're favored in equilibrium, that means that that's the side that is going to be formed more of. So in equilibrium, you always have some of your reaction going forward, some of it's going backward, but whatever makes the more stable product is going to be favored.
Is on that one, right? The OH can resonate and do more of these things. Because in that.
Do we compare pK value for the first one?
Yeah, I would say PK is the way to go on that one. Silly little thing about REO, you use it sometimes and you're like, oh, atom resonance, but sometimes it's wrong. And that's just life. So when in doubt, use pKa's. And for the first one, if you're gonna have to use pKa's. So let's look those up right now.
They're gonna be provided.
If you're directly asked to like determine which side is more acidic based on pKa's, then you will have them. Otherwise, it might just be based on REO, but if they're asking you to use REO, it's going to be ones that will hold true to REO. But every once in a while, there's like an outlier that just doesn't really work that well. So let's see, our acidity of this acid is going to be -7.3. That's a pKa. I think that's right? Yeah. And then our H3O plus is going to be negative 1 point. That's the wrong side. Hold up. Negative 1.73 is the acidity of our hydronium. So based on that, which side do we think is going to be favored? You're saying the products.
Shift towards the more acidic one, right?
So here's the confusing thing. When you're looking at Oreo, you focus on your conjugate bases, right? And on those, you figure out which side is more stable. So whatever side has the more stable conjugate base is favored, right? But if we're using pKa's, we have to look at our acids, which makes it a little tricky here. But if we're looking at our acids, which one is more acidic between hydronium and then our like carbonyl acid? The more negative one, yeah. So this little carbonyl acid thingy over here is going to be more acidic. So what does that mean if it's more acidic? Not necessarily, it'll form a more stable conjugate base. But what does that mean about, it's like, okay, it's more acidic, what's going to happen then?
It'll be less.
Yeah, so if this over here is more acidic, then we're going to be pushing towards the other direction, right? If it's more acidic, it wants to lose its proton. So we're then going to form the product of that, which is this side. Does that make sense when using that versus Oreo? Okay, just, yeah, remember if you're using pKa's, look at acids. If you're using Oreo, look at conjugate bases. It's confusing. The more you work with it, the more it'll come to you, but I was really bad about flipping them up when I was first doing it. So fear not, it's okay. What about this next one? This one you could kind of do. Oreo would be kind of tricky on this one too, but you could kind of use it, or we can do pKa's.
Oh, we're supposed to be.
Yes, yes and no. Oreo is tricky because sometimes you want to look at the acid first and you think that that's the most important thing, like period. But then resonance right after it, and sometimes that can be more important and more contributing to which side is acidic or not acidic.
So when
Yeah.
it would just be better to use pKa.
Sometimes yes, sometimes no.
It is more accurate than Oreo, but I can say for hydrogen too, yeah.
Yeah. Let's, okay.
Depends.
I'll explain this one like area wise instead of using pKa's. So if we're looking at this conjugate base over here, our hydroxide, that is stable enough because we have our negative charge on our oxygen, so that's good. But that's all that we have, right? So our atom is good, but that's it. If we look over here, we have our little lone pair on our carbon, which it looks initially like that would be less stable, right? Because our charge is on a less electronegative atom. But if we think about it here, we can push our charge up onto one of these carbonyl groups, or we could push it up onto the other one. Right? So then we have multiple different structures that we can form, right? So we have our charge stabilized and moved around, but we also have two of those structures that have our negative charge on oxygen. So that's going to be more stable than just having it on oxygen right away. So knowing that that's more stable, which side is favored? Yes, our products are favored on this one. Does that? That one did work with Oreo, but you just have to think through all of Oreo and not just stop at atom. Because initially it looks like it would be the other way around.
You just mean like you have to go through them, check.
Yeah, always check for resonance at the very least before you move on. Because yeah, sometimes it'll play little tricks on you. And then, okay, so that made sense though. Okay, so that was our last one, and it's only 9:03. That could have been worse. I'm so sorry it was late, but so please fill out for any feedback you may have. We'd love to hear it.